This is the last part of chapter 14 on the Diels-Alder reaction. We're going to cover stereochemistry, regiochemistry, and then just a little bit about UV spectroscopy. Stereochemistry of the Diels-Alder reaction generates up to 4 new stereogenic centers. So that means you can have 2 to the 4th or 16 possible stereoisomers. Now that wouldn't be very useful if you're going to get 16 products, but usually there's just one major isomer and it's an enantiomer. And this is determined by 2 things. The first is geometry of the dienophile or the alkene. If it's cis, then those groups will be cis in the product. If it's trans, they'll be trans in the product. So that's easy to identify. And then the harder one is the endo rule, which determines the other 2 stereogenic centers. If I look down here, I've got a diene with substituents on all 4 carbons. If I react that with a trans dienophile, methyl and the carbonyl are trans. In the product, this is shown in red, the part that came from the dienophile is in red, and the methyl is trans to the carbonyl. If I react the same diene with the cis alkene, now the carbonyl and the methyl are going to be cis to each other. So again, that's the easy centers to identify. If I have substituents at 1 or 4, then I'm also going to generate 2 more stereogenic centers. And that's what the endo rule explains. The endo rule, your book, and a lot of books explain this just in terms of bicyclic systems, but it applies to all Diels-Alder reactions. And the real rule is that the major product comes from the dienophile orienting, so the electron withdrawing group sits under the pi system of the diene. There is a handout in D2L under content that explains this, and that's what this figure comes from. So if I have a diene with a methyl at 1 and a methyl at 4, I react that with the cis alkene. The carbonyl and methyl that were on the alkene are going to be cis. And what the endo rule tells you is the stereochemistry between the carbonyl and the substituent at 1. And for the endo product, that's going to be cis. For the exo product, which would be minor, that would be trans. So the alignment is shown underneath here. If you look at the diene lining up with the dienophile, the p orbitals that are on carbons 1 and 4 have to overlap with the p orbitals of your alkene. And in the endo alignment, the carbonyl sits underneath the pi system. In the exo alignment, it sits outside the pi system. Same thing if I reacted the same diene with a trans alkene. Now the substituents on the alkene are going to be trans, and with the endo product, the methyl at 1 is going to be cis to the carbonyl. With exo, it would be trans, and again, I've shown the alignment. So it could be hard to picture that alignment, and an easy way to predict the endo product is to look at the inner and outer rim of your diene. So the rule is that the substituents on the outer rim of the diene will be cis to the electron withdrawing group. Electron withdrawing groups on the dienophile would be a carbonyl, a nitro, a nitrile. Those all have a full or a partial positive charge. And if I look down here, I've drawn the diene and this line sort of through the pi system of the diene. And on the outer side is where the methyls are. And on the inner side or the inner rim is the hydrogens. So the methyl on the outer rim, 1, is going to end up cis to the carbonyl. And that's this stereochemistry right here. The substituents that are on the outer rim are going to be on the same side as each other. So if that methyl is up at 1, then the methyl at 4 is also up. So this would be an adduct with 4 new stereogenic centers, but you're going to get just one major product. If you look at something that will form a bicyclic system, cyclopentadiene is a very reactive diene because it's locked in the S-cis conformation, and it reacts with the dienophile to give Diels-Alder adduct. So if I draw this rim through the diene system, the hydrogens are on the outer rim, and the CH2 bridge is on the inner rim. So the hydrogen is going to be cis to the carbonyl. So I could draw this out either in a three-dimensional drawing or a more conventional flat sort of drawing. And the hydrogen is cis to the carbonyl. They both point down. And the CH2 in the middle points up. So that is how you can predict what the major stereoisomer in the Diels-Alder is going to be. The reason for the endopreference comes from the molecular orbitals. Again, there's a handout on D2L. If you were in my class in 3010, we talked in the very beginning about molecular orbitals, and these are the molecular orbitals for a butadiene system, or a diene where you've got 4 p orbitals conjugated. So I have 4 molecular orbitals, pi 1, and then pi 2, and then the antibonding orbitals would be pi star 3 and pi star 4. The 4 electrons go 2 into pi 1, 2 into pi 2. So my second one, pi 2, is called the HOMO, the highest occupied molecular orbital. And then the first one that's empty is pi star 3, and that's the lowest unoccupied molecular orbital, or the LUMO. So in any organic reaction, what's really reacting is your frontier molecular orbitals, and that is the HOMO and the LUMO. So the highest occupied orbital is donating electrons into the lowest unoccupied orbital of the other reactant. In the Diels-Alder reaction, the HOMO of the electron-rich diene adds to the LUMO of the electron-poor dienophile. So if I map these molecular orbitals on here, I've put pi 2 onto the diene, and then pi star 3 is the LUMO, and that is mapped onto the dienophile. The orbitals that are overlapping to make the new sigma bonds are these p orbitals where I'm drawing in the dashed lines, and they have to have the same phase in order to combine, make a new bond. If I put the endo alignment, that's what I've drawn here, the carbonyl sits under the pi system, and you have this extra stabilizing interaction in the back there, and that is what holds the dienophile in the endo alignment. Even though it's more sterically congested, you have this electronic stabilization. So that's stereochemistry, and then another aspect of the Diels-Alder is the regiochemistry. And if you have electron-releasing groups on the diene, these would typically be alkoxys or amines, those have lone pairs to donate, or alkyl groups are weakly electron donating. So your electron-rich diene is going to react with your electron-poor dienophile. And you have to look at the resonance forms of each one to decide which end adds. So the dienophile is always going to have a resonance form that puts a plus charge at the beta carbon, beta to the electron withdrawing group, 2 carbons away. On the diene, it depends where the substituent is. If you have a substituent at 1, you can draw a resonance form that puts a negative charge on 4. If your substituent's on 2, then the negative charge is on 1. So for a 1 substituted diene, carbon 4 is more rich. For 2 substituted, carbon 1 is. So that's going to determine which way they add. So the upper example here has a methoxy on carbon 1. That makes carbon 4 the most negative. That end wants to add to the beta carbon of the dienophile. So I'm going to get one major product, not the opposite regioisomer where the methoxy would be 2 carbons away from the carbonyl. And this is the endo product that's shown. The methoxy is on the outer rim, and that is cis to the carbonyl. If the substituent's on 2, the electron donating substituent, then that means carbon 1 is more electron rich, so that's the one that's going to add to the beta carbon of the dienophile, and the product on the left is going to be my major product, not the one on the right. So that's all we're going to cover with the Diels-Alder reaction. Just a little bit on UV spectroscopy. So the frequency of UV light is 200 to 400 nanometers. And what happens when you shine UV light on an organic compound is it promotes an electron from ground state to excited state. And one of the most common transitions is a pi to pi star. So there's an energy gap between those orbitals, and the lower that gap, the longer the wavelength of absorption. So down here on the left, you've got, again, the molecular orbitals of 1,3-butadiene, and this is the pi to pi star gap here. So when you shine UV, you're promoting an electron from pi 2 into pi star 3. And that energy, you can use this formula, but it's inversely related to the wavelength. For 1,3-butadiene, the strongest absorption, or the lambda max, is at 217 nanometers. If you look over here on the right, you can see a comparison where the second one is 1,3-butadiene. You've got this energy gap. As you increase conjugation, that gap gets smaller. So if I went to the one farthest to the right, where there's 4 alkenes conjugated, now it's all the way up to 290 nanometers. So there, before NMR, you still can use UV spectroscopy to indicate what kind of conjugated diene systems are present. Although usually what it's used for now is just an analytical tool as a detector on chromatography systems. So one other application of this is dyes and colored compounds. So compounds that have extended pi systems actually can absorb all the way up in the visible range, 380 to 780 nanometers, and that gives colored compounds. So beta carotene, has this very long extended pi system, and the lambda max is all the way up at 455 in the visible region. So it absorbs blue light and it appears yellow, or orange, that's the color that you see in your carrots and tomatoes. Another example, you can look up the structure of chlorophyll, but that's also a highly conjugated system, and it actually has 2 absorbances. It absorbs in the blue and it absorbs red, so what's left appears to be green. So your leaves appear green because it has 2 UV absorbances. And that is where we're going to end chapter 14.